Well, good morning, everybody. My name is Glenn Klingenpeel, and it is a pleasure to be with you this morning, even if it is virtual and through a pre-recorded presentation. But I hope everybody is safe and healthy and finds this presentation helpful. So it is just a product of the world in which we find ourselves today. But I am here today to talk to you about flooding the Trinity River and the Region 3 Flood Planning Group. I'm going to do this under three major areas. I'm going to give you an overview of the Trinity River Basin, discuss the factors affecting flooding in the Trinity, give you some quick examples of recent flood events. I think we're all very familiar with those. And then kind of end the presentation by talking about the Region 3 Flood Planning Group that started here just at the end of last year. Talk a little bit about the structure and the members of that organization, the objectives, and of course the timelines. The cute little picture down at the bottom right of this fortification or this settlement, something I ran across looking at the Wall Street Journal a couple days ago, and I thought, you may think about flooding too much. If you're looking at the Wall Street Journal and a random advertisement for a strategy game that you'll never play, I never have played, pops up, and the first things you think of is, man, what a terrible place to build a settlement, right? It looks awesome. It looks like it's highly defensible. You've got this one bridge that comes into it, but what happens the first time that it floods? That settlement is just going to be wiped off of that island. So I thought that would be a good way to to kick things off. Moving now into an overview of the Trinity Basin. Here is the Trinity Basin. It's about 18,000 square mile watershed. It's a little bit less than that. Depending on where you start measuring, it's about 713 miles from the headwaters of the West Fork all the way down to Galveston Bay. If you look right up here, you'll see that near the headwaters of the Elm Fork, it literally comes within a couple miles of the Red River and Oklahoma. We've got this very large metropolitan area, the Dallas-Fort Worth area, with a population of about 7.5 million people. That's a lot of impervious surface. It's a lot of rooftops, a lot of parking lots and streets. And obviously that has had a huge impact on the flood dynamic in the Trinity Basin. City of Houston sits just outside the Trinity Basin, obviously not directly affected by flooding, but very dependent upon the Trinity for water supply. And then of course we've got Lake Livingston sitting near the bottom of that basin, kind of like a funnel through which all of this water has to pass as it moves down through the Trinity. Looking at the variability of rainfall across the basin, there's a tremendous amount. We go from about 32 inches average annual rainfall in the far northwestern corner, all the way up to about 60 inches in the southeastern corner of the basin. So again, tremendous amount of variability moving roughly from west to east. So yeah, almost twice as much rainfall across the basin. And of course, we've had our fair share of flooding events, and thanks to the Corps of Engineers for this slide and the next slide. And those significant floods occurred in 1908, 1942, 49, and I think we can safely add now 2015, 2017, and 2019. The Corps had planned originally about 21 dams, not about, exactly 21 dams in the basin, of which they built 8. The first to be built was Lake Grapevine. That was back in 1952. The last was Ray Roberts back in 1987. Collectively, those reservoirs, which I think every single one of them has a combination of conservation and flood storage, have about 2.2 million acre feet of conservation storage, and that's water supply storage, with about 1.5 million acre feet total of flood storage. Of course, the way that that works is they'll catch those flood flows, they'll store them, and then release them gradually after the flood event has passed, so they can safely then renew, if you will, that flood storage capability or capacity, so that when the next storm comes, they'll have that available to catch those flows. That's a common misconception that we battle all the time. I was looking for a better word, but I guess that's the right one. Is that, if you've got a reservoir, regardless of whether it's flood control or water supply, they're somehow interchangeable. You've got this water supply reservoir, and somehow magically you're supposed to be able to use that for flood control. Obviously, it doesn't work that way, because a water supply reservoir can only operate in one of two capacities, right? It can either be full of water, in case you've got a valuable water supply there, and that was the purpose of building the water supply reservoirs, or it can be empty, so that you've got flood capacity or storage capacity to capture those flood flows, but they cannot work in some kind of flexible either or scenario. It is either one or the other. It's a true binomial proposition. The cost in 2013 dollars of building these reservoirs, that was the 8 that were actually built, was about 1.67 billion. Again, that's in 2013 dollars. The benefit that the Corps estimates from having operated and built these reservoirs is about 72.3 billion. That gives you a benefit to cost ratio, a very impressive benefit to cost ratio of 43.2. Looking at where these reservoirs are situated, you can see that they're basically the gatekeepers to the Dallas-Fort Worth area, and that makes a lot of sense. Obviously, there's a lot of people in that area. There's a lot of infrastructure that needs to be protected. And so the shaded area that you can see to the north and to the west, by and large, those are the watersheds that are controlled or protected. I don't like the term controlled, though we use it often because it's a little bit misleading, that are protected by these flood control reservoirs. And of course, you've got Joe Pool Lake down here just to the south of the Metroplex. And then a component that is often overlooked is the Fort Worth and the Dallas floodways. You know, there are a network of canals and storage capacity, conveyance capacity that as you move through both of these cities, that is a significant component to the Corps' infrastructure here, the flood risk reduction infrastructure that they operate. And as I mentioned earlier, the way that they operate is that they catch these flood flows and then they release them over time after the peak of the flood has passed. And so that's what I wanted to talk about and show here is that, and what you're looking at on the graph to the right is the relationship between the flow in the river and the travel time that it takes those flood flows to make it from Dallas down to Lake Livingston. And a common misconception is that the more flow that you have, the faster the water moves. And of course, we know that's not true because once you get out of that channel, and that's the graphic that you're looking at to the left, Hydrology 101, once you get out of that channel, your roughness coefficients go up. You've got to move around trees and grasses and other obstacles, so it actually slows it down. Once you've filled up that capacity, though, then it does start to pick up. The point here is that when you're looking at flood flows, you know, between 30,000 and say 60,000 CFS, it can take over 2 weeks for water to flow from Dallas to Lake Livingston. So those flood flows that are released from the reservoirs can be in the system for an awfully long time. And hopefully that's happening somewhere south of 20,000 acre feet cubic feet per second, because that's the Corps' target is obviously not to make flooding worse. Nevertheless, that water can be in the system for a very long period of time, and that's one of the conversations that we've had with downstream landowners is the operation of those flood-controlled reservoirs and what role they may or may not play in the flooding that we've seen over the last 5 years. So that brings me to my next item, and that's factors that are affecting the flooding. I've already talked about a couple of those, so really I'm going to focus on weather from here on out. And of course, factors we've already talked about are the development, the increase in impervious surfaces, and the operation of the flood control reservoirs, though those have obviously had a huge net benefit, but they do change that flooding dynamic just a little bit, the characteristics of the flooding, if you will. So obviously the weather is the big determining factor here. And in north central Texas, this is driven by convection systems, and those come basically in 2 flavors. As these frontal systems come through, we can get these supercells or these squall lines. And, you know, I remember back in 2015, I'm going to talk more about that in just a minute. You know, it seemed like every day you'd look at the radar and there was another squall line coming through that was just dumping a tremendous amount of water on the area. So, and typically that's what we'll see in the Dallas-Fort Worth area is a limited number of events that are producing a tremendous amount of rainfall. We do have a little bit of topography here, and so that can run into those natural conveyance systems, which then can surcharge, creating downstream flooding. Obviously, that becomes more pronounced as then you move into the middle and lower Trinity. What we see on the coast is a little bit different from that when we get these strong tropical systems that can sit there and just dump a tremendous amount of rain over 1, 2, 3, 5, 7 days, and even longer when you're talking about a system like Harvey, a very, very unusual system. And that water is simply falling too fast and too broadly over flat topography to make it into those natural drainage ways. And so you get pounding and you get flooding over very, very large areas. So here we are with our supercells and our squall lines that produce a lot of rainfall. No surprising, and again here in the Dallas-Fort Worth area, the North Central Texas area, no surprising that there's a strong seasonal component to this. It isn't spread out over the years. What we're looking at in this graph is the average annual rainfall as recorded between 1981 and 2010, so 20 full years of data. And of course, that does stop in 2010, but there was a pretty good mix of dry years and wet years in that data set. So we feel like this is pretty representative, at least for now. Things may be changing, but we feel like it's representative, at least for now. And so what we see is a bimodal distribution where we have these convection systems that are coming through in the springtime and then not at all in the summer. Typically, we'll have a high pressure system that'll develop over Oklahoma and it keeps those frontal systems at bay, but then picks back up in the fall, September and October when we get those frontal systems coming back through. And no surprise then that that's when we see the majority of our precipitation. Nevertheless, I think it does surprise a lot of people when they see that October is actually the second wettest month of the year. And then January actually being almost tied for the second driest. I think it actually beats July. And I think that surprises a lot of people too, because they think of winter as a very wet time. And I'm not exactly sure why, probably just because of the colder temperatures. But no, most of the rainfall occurs in just a couple of months over the spring and then back into the fall. Not only do we have a tremendous amount of variability between months, but we can also see a tremendous amount of variability between years. And so what I'm showing here is the exact same data. Those blue bars and with the hash marks in them are modeled coloration, if you will. I've changed the scale here so it looks a little bit different, but it's the same data, I promise. Put on top of this or next to it is the rainfall data from 2014. And again, this is for each one of the 12 months of that year. And you can see really how dry 2014 was. And keep in mind that 2014 was actually the last year of a 4 to 5 year drought, depending upon when you start that drought cycle. I tend to start at the beginning of 2010, and so you get 5 full years of drought. So what we see here is a distortion of that bimodal distribution of the rainfall. And I don't know what happened in August, but you can see just how high the rainfall was there, anomalously high in August, but every single month except for August, we had significantly less rainfall than normal. What I want to do now is just take a look at what changed within 1 year. So that's 2014 versus the average. And let's put on top of that graph then the 2015 data. And you can see that our bimodal distribution is back. And look at just how exaggerated that distribution is. Of course, with May, which was just a crazy wet month, we got in that month alone, we got about half of the normal precipitation for a year, half in 1 month that we'd normally see over the span of 12 months. And then it just kind of went away in June, July, August, and September. Those were all dry. Well, July, August, and September particularly were extremely dry. They called it, as a matter of fact, this flash drought. So you can see how the nature of the distribution of rainfall can change from year to year as well. Looking at this in a different way is this graph, and it takes a little bit of explanation, but I think it's worth it. I modeled this graph off of the famous Menard graph. And what we're looking at is the cumulative amount of water that was flowing down the Trinity and past the USGS gauge at Rosser. So you start on January 1 with 0, of course. That's when we start measuring. Then you go all the way through the end of December, which gives you a full 12 months of flow past Rosser. And if we look at 2014, which is the red fill, you can see that we had less than 800,000 acre feet of water, total water for the year, that flowed past Rosser. If we compare that with 2015, just 1 year later, just 1 year later, we see that we had over 8 million acre feet of water that flowed down the river at the exact same spot. So from 1 year to the next, we increased flow by a full order of magnitude. Something else I'll point out about this graph, if you remember that drought that we were just talking about that happened, that flash drought that happened in July, August, September of 2015, you would expect to see, all things being equal, that the amount of water flowing down the river would virtually stop. You wouldn't be adding any more. Okay, it would stay constant. That graph that you're looking at right there would flatten out. What I'm showing with these two arrows that are on the graph now represent the releases of flood flow from those upper core reservoirs. And remember, they've got in total about 1.5 million acre feet of flood storage. And we see here that well over 1 million acre feet of water flowed past Rosser in the middle of this flash drought when it basically wasn't raining. And I remember that's when the magnitude of the rainfalls that we saw in the spring of 2015 really dawned on me, when it kind of clicked, so to speak. I was driving over the Trinity River Bridge in Dallas, and it was incredibly dry. We were in an agricultural drought, which meant the soil was very, very dry, very little soil moisture content at all. And yet the Trinity was full. It wasn't flooding, but the Trinity was bank full, and all that because of those releases coming out of those core reservoirs. And I remember thinking, can you imagine what would have happened if all this water that we're watching flow under the river in a very dry period had been compressed, and those flood flows during May and June of 2015 had gone as a peak, as an unaltered hydrograph through Fort Worth and Dallas? And I think the damage just would have been catastrophic. I know the Corps has some numbers as to what that damage would have been, and as I recall, it was well in excess of $1 billion. So it would have been catastrophic flooding. As it was, there was very little flooding in Fort Worth and Dallas from the Trinity surcharging in 2015, which is absolutely remarkable. But I really like this graph because you can discern a lot from the shape of that graph, and you can see in May how it enters that exponential growth phase or increase, and of course that's all of those convection systems that were coming just day after day after day and dropping all that rain on us. So yeah, it's been a rough 5 years. 2015 was just the first year where we kicked off this very wet cycle, and of course that spilled into 2016. That's a picture of the Trinity River. I remember flying over it in an airplane, and a gentleman beside me said, "What lake is that?" And my answer was, "That's not a lake. That's the Trinity River." It was carrying a tremendous amount of water, as we saw from that last graph. Then in 2017, we had, of course, Hurricane Harvey, which was the wettest, the most rainfall that had ever been recorded over the continental United States, and I think that even beat Hawaii. So that was the largest storm that we've seen in the United States, and you can see those rainfall totals in the smaller graphic to the bottom. That was an estimate of discharge that we were calculating from the Trinity because of that storm, and it was just it was ridiculous in terms of the amount. So 2017 we got hit by Harvey. 2018 we had very significant rain events in February, and then September and October, which produced flooding. This is a picture of the Trinity from 2018. And then, of course, in 2019, we had Tropical Storm Imelda, which, coming just 2 years after Hurricane Harvey, was just insult to injury. And that tropical storm dumped upwards of 40 inches in parts of the lower Trinity Basin. So, it's been a very, very tough 5 years. And what is notable about this, most notable, other than these record-setting storms, of course, was the fact that it came just immediately after these 5 years of drought. So you've got 5 years of drought, and not just drought, bad drought. 2011 was both the driest and hottest year on record. Of course, you have to keep in mind that records only go back 150 years or so, but both hottest and driest year on record. And then that lasted all the way through 2014. So 2010, 2014, very severe drought, then followed immediately by 5 years, 2015 through 2019, of record-setting, unprecedented flooding. And so we've created, because of the juxtaposition of the drought and the flooding, this strong perception that something has changed. And I'm not saying it hasn't, but we know that at least one thing did. And that one thing that changed was we went from La Nina to El Nino. And what we see is that those patterns have a very strong impact on the climate in Texas, on the seasonal weather patterns in Texas. And so that's what I'm trying to display here with this graph. And this is a graph I was just kind of playing around with. I wanted to see if something would pop when I put this graph together, and I was just amazed at how well it did. So let me explain it. It is a little bit complicated, but I think it's worth understanding. So we have January 2000 all the way through September of 2016 on the x-axis. On the y-axis on the left side, we have the percent of the state of Texas that was in some level of drought, and that can go everywhere from or anywhere from unusually dry all the way up to exceptional drought. So just some degree of drought. So the higher that red shading is, the more of Texas was in a drought. On the right y-axis is the inverse oceanic Nino index, or the SST. Okay, so this is how we determine whether we're in a La Nina or an El Nino. And I've took the inverse of this just so the movement of the data in these graphs is moving in the same direction, so it's a little bit easier to interpret. So the higher those blue bars are, indicates colder surface water temperatures in the Pacific, the El Nino region 3.4. And the threshold to be in La Nina is 0.5. So you can see that starting over in January of 2000, we were significantly above that. Okay, so the further those blue bars drop below zero, the warmer that sea surface temperature is, and the stronger the La Nina event is, or El Nino, sorry, the El Nino event is. And what we see is a remarkable pairing of the data. And obviously this is a qualitative analysis, but the correlation is unmistakable. When we're in La Nina conditions, we experience more drought. When we're in El Nino conditions, we experience significantly less drought. And of course, there's a little bit of an offset, and you would expect that because a drought doesn't start the last day it stopped raining, right? It takes a little while for the drought to build. So you expect to see a little bit of an offset, and obviously it takes time for those convection events to start building, that deep convection over the ocean to start building and pumping moisture into the atmospheric river as well. Okay, so moving now on to flood planning. After the 5 years of drought, followed by 5 years of flooding, there was a huge appetite in the legislature, because that flooding didn't just happen in the Trinity Basin, it happened across the state of Texas. It was a huge appetite to do something. And so the last legislative session, the 86th legislative session, passed Senate Bill 8. They actually passed a slew of flood bills, but Senate Bill 8 is the one I want to talk about. That is what established the flood planning process. Specifically, it directed the Texas Water Development Board to stand this whole process up. And it is by design very, very similar to the water planning process that has been so successful in Texas. And so Texas Water Development Board, then acting on Senate Bill 8 and the direction of the legislature, created these 15 different regional planning groups. So just like water planning, this is going to be a bottoms up, a ground up approach to flood planning. So we have these 15 planning regions, and you can see the Trinity is region 3. I showed you where that was earlier, so hopefully you can find that. And we call that, again, region 3, and it is one basin. So the legislature, they took comment, and at the end of the day, decided to keep the Trinity Basin as one planning group. And I think the logic behind that was the fact that the legislature was very aware that when you're dealing with flooding and flood risk reduction and flood control structures specifically, one person's solution can be another person's problem. So if I fix my flooding by just putting a couple levees on my river section, what's going to happen is it's going to accelerate the flow of that river downstream, so it's going to compress that hydrograph, and you're likely to make flooding worse downstream. So by keeping the Trinity as one planning group, I think the idea was to bring all these stakeholders to one table so that we could make sure that there was accountability in the solutions. And I think also to head off this upstream, downstream division that might otherwise become problematic. And one of my goals as the interim chair of Region 3 group is to prevent that from happening. And I think that's very, very doable. Okay, statutorily, each one of the planning groups is required to have 12 different interest categories. And you can see those over to the right: agriculture, counties, electric generating utilities, environmental interests, flood districts, industry, municipalities, public river authorities, small business water districts, and water utilities. So pretty good cross-section, I think, of representation. Those 12 interest groups represent the voting members who will actually act on things that come before the planning group. There are also 7 ex officio members, and they're representing state agencies. Texas Water Development Board appointed individuals to fill these slots when their board met on October 1. The voting members that we have for the Region 3 Planning Group include Lisa Shepard, she's representing counties, Samuel Blocker with electric generating utilities, Jordan Maka with environmental interests, Rachel Eichert with flood districts, Matt Robinson representing industries, Sarah Staniford municipalities, Andrew Isbell representing the public, myself representing river authorities, Gerardo O'Connor representing small businesses, Mike Rickman representing water districts, and Scott Harris representing water utilities, which I think is a very good cross section in terms of representing different interest categories. So I think the Texas Water Development Board did a very good job there. The non-voting members include Adam Wisnett with Texas Parks and Wildlife, Brian Hertick with the Texas Division of Emergency Management, Rob Barthen with the Texas Department of Agriculture, Steve Bednars with the Texas State Soil Water Conservation Board, Jonah Chen with the General Land Office, Richard Bagans with the Texas Water Development Board. He is our primary contact with the Texas Water Development Board. And then Kevin McCullough with the TCQ, the Texas Commission on Environmental Quality. The Region 3 Flood Planning Group met for the first time. We convened on October 27. It was a 3-hour-long meeting. It was a long meeting, but we got a lot of work done. During that meeting, the Trinity River Authority was selected to serve as the group sponsor, which really means we get the privilege of doing all the administrative work. And it's a pretty heavy lift, especially in the beginning stages as we're trying to stand this group up and get everything running. We have to date prepared and submitted a grant application, and we're preparing requests for proposals to select a primary consultant as we speak. Actually, hopefully by next Monday, the 11th, those will have gone out, but we'll see. Also, during that meeting on the 27th, the group voted to add 3 additional ex officio non-voting mandatory members, and those members will represent the Corps of Engineers, FEMA, and the National Weather Service. We met again on the 17th of December. During that meeting, we created a nominating committee to fill the vacant agricultural slot, and we also discussed methods for soliciting and selecting a technical consultant. So what is the group supposed to do? Well, in a highly summarized fashion, at a very high level, 3 things really: determine flood risks, evaluate and prioritize risk reduction strategies, and then compile a regional report that will be sent to the state, where it will be rolled up into a single statewide document. So again, you're probably seeing a lot of the similarity between the flood planning process and the water supply planning process. So the Texas Water Development Board has put out a work plan that has 10 tasks that describe in very great detail how to accomplish those 3 primary things. And I've highlighted just 3 of those tasks here that I think pair up with the 3 that I mentioned on the previous slide: existing and future flood risk analysis, recommendations for flood management, evaluation strategies and projects. That to me is really where the rubber meets the road. And then of course, to put all that together in a plan and forward that on. Of course, all the other tasks there are very important that will support these items and others. In terms of timeline, we've got a lot of work to do, and we don't have a whole lot of time in which to get it done. As I mentioned, we met for the first time on October 27. By February, we hope to be entering into a contract with the Texas Water Development Board. And then immediately, really not even waiting for that to happen, starting now, soliciting technical consultants, and hopefully those will be in by the end of January. So by mid to late February, we can actually be selecting a technical consultant or have that selection done, and then begin negotiations so that by the end of March at the latest, April 1, finalize that technical consultant contract. And we're very, very anxious to get that done, because that is really where I think the true work of this group starts getting accomplished, right? We move past the standing it up, the administrative phase, into a lot of the more technical work. And I think everybody's very anxious to move into that phase. So let's assume we get that done April 1. We start on that work. January 7 of 2022, our technical memo is due to Texas Water Development Board. And August, middle of the summer of 2022, that's just next year now, those draft regional flood plans are due to Texas Water Development Board. That is draft, but that flood plan is due to Texas Water Development Board. So less than 2 years from now. Again, a lot of work and not a whole lot of time in which to get it done. January 10, 2023, those first regional plans are submitted to the Texas Water Development Board, and by September of 2024, that first flood plan, after they've been all rolled up and vetted, should be finalized. And with that, I think I will stop here, and hopefully we've got time for questions. All right, thank you very much.